Hello, Mikolaj. Thanks for coming on the podcast today.
Hey, nice to be here for sure.
Yeah, I'm looking forward to our conversation today. So, for people who might not know who you are, you're a geneticist and founder of the company Merogenomics, where you do human genome sequencing for its application in the medical field, and you're a proponent of incorporating these various sort of genetic screening tests for people to employ in their own lives in order to get a really good understanding of their genetic and biological makeup, which can, give all sorts of useful, potentially life-saving information. I've done a genetic test like this as well, and it's brilliant. I mean, you just learn so much about, your sort of biological makeup, and it really informs how I do things now, how I eat, how I sleep, how I exercise, what medications I can take. And so I'm really excited to talk to you today. So thank you again. So I'll tell you what,
Cheers, pleasure to be here.
Yeah. So let's start off with just a little bit of an overview of, why did you get into this field specifically? Not just genetics, but in terms of, the sort of consumer side of genetic sequencing.
This whole idea to get into genetics, medical genetics, especially in a format of being able to bring it to consumers, actually started during my doctorate degree, because it was during that time when the technology came out to the market. So this was a while back now, over 10 years ago. At the time, it was exceedingly expensive, but I instantly recognized the value of it and its importance in the future. Because prior to my doctorate degree, I actually had a degree in genetics. So I was already interested in this topic and had some scientific background of it. So I understand the value of it, because in a way, you can think of full genome as a program code that runs you. So then you can appreciate that looking into your program code could be of value. I was instantly fascinated and thought, hey, if you're going to try to stick with doing something you absolutely love that is tied to also sciences, which I was very well trained, this is definitely a great area of interest for myself.
Right. It's an interesting comparison, or a way to think about genes as, program code, because, essentially we're biological machines, right? It's one way of conceptualizing what a human being is, or what any living creature is for that matter, I suppose. We're just sort of fairly complex, or very complex ones. But for me, what's remarkable is how, in a single cell, right, where you have your DNA, that has all the information that can make up your exact, being specifically, which is just insane that that's a thing and that it's possible in that capacity. And I don't even really understand how that works. Like, maybe, could you help shed some light on that? Like, how is DNA, what does it mean when people say that information is stored in DNA?
So, first of all, DNA is the greatest storage of information. So there's no other way of storing information that is more compact and more efficient than the DNA itself. So the way it works, the best way I could maybe explain it is, when we think of computer programs, the code itself is just a series of 1 and 0s, correct? We're all kind of familiar with that concept.
Yeah.
Same thing with the DNA, but instead of series of 1 and 0s, now think of it's 1, 0, and then 2 and 3. So you actually have 4 numbers instead of just 2, as in a computer program. So that means the coding is more complicated, but it gives you greater capacity of being even more concise of how you store information, and then substitute the digits from 0, 1 to 3 into actual chemicals. So DNA is made up of 4 different chemicals, And then it's the arrangement of these chemicals that is the storage of information. So just like this recording is digitalized, then it will become series of ones and zeros. Same thing with this recording, you could actually put it into the DNA. As long as you define as what that one in the digital recording would be versus zero, you can put it into DNA. And that has been done. So you can record movies into the DNA as well and store it. So the reason why it's such a compact way of storing information is because a single bacterial cell could hold tons and tons and tons of movies, for example. So then you can see how compact of a storage of information it could be.
So what do you mean when you say that they've put videos into DNA? Like, yeah, I don't really know what that means.
You can define what each, say, for example, each pixel color is. You can define what that pixel would be in terms of genetic code. So, for example,
right,
you could say, so the four chemicals, they are A, C, T, and G. That's the abbreviation. So you could, for example, define that, and I'm just going to make up things. ACT means one thing, but TAC means something else, and then so on. So you can make these combinations and define that they will actually mean this color of a pixel in this specific location. So you can code everything that way.
Right. I see what you're saying.
And then afterwards, when you decode the DNA and you know what the code means, you can recreate the movie.
Right. Okay. I see what you're saying. So it's like you code specific things in the format of DNA as opposed to in the form of like binary code. And then you can decode that to reconstruct Correct. What that particular sequence not symbolizes, but creates, I suppose, what that information makes.
And sure, you could say symbolizes. You would still have to have a system that then decodes the DNA and transforms it into some form of a visual output.
Right.
So then you'd still need to have a system to do that, but it allows you to store that information as such. So once again, with a genome, you could put tons and tons of information.
Right.
So you could put an entire library of all books ever written by humankind into a petri dish, if you will.
Yeah. I mean, it's truly remarkable how much information can be stored in, a human genome. I mean, is there a figure that you're aware of that makes sort of sense in computer science-y terms, in terms of gigabytes or terabytes or something like that?
Not in terms of how many, say, YouTube movies, and I'm sure that has been done.
Yeah.
But normally when you decode human genome, that's the only information I'm familiar with because that's my background.
Sure.
It takes approximately 100 gigabytes of storage power just to store your own human genome if we were to be decoded.
Wow.
However, I can tell you that in terms of the greatest output of data in the world, physics will be one of the greatest ones in astronomy. YouTube and Facebook will be in the top 5 for sure. And so is genomics.
Yeah.
So in terms of data capture and information, it ranks as one of the top ones and likely will become one of the top ones, if not the main one in the world in terms of how much data it produces, just because of how much data we store in our own genome. And it makes sense because it's a program code that has all of the information to determine how you as a human being will be built from a single cell, from a single egg that was implanted by a sperm cell. From that single cell, there is a program code to create you. And then eventually you are trillions of cells. So all of that has to be coded in one place. So that's your development. And on top of that, that same code has to also determine how you run on a daily basis.
Right.
So you can appreciate how enormous of a program code it has to be.
And continually adapt to changing environments and stimuli and things like that. Which I guess, you know.
Exactly. That's
yeah. No, go
That's
ahead.
what I mean by how you run every day, because you have to be able to respond to the outside environment instantaneously all the time.
Yeah.
And that's how you respond is based on that code.
Right. And I suppose this is why epigenetics is so interesting as well, because from my very uneducated understanding, epigenetics is the study of how the environment influences which genes are activated at any given moment, which then reflects the changes physiologically or psychophysiologically, if you want to look at it that way, in your, personhood, I suppose. Yeah.
I really like that summary. Yeah, that's exactly what it is. It's epigenetics is how do we respond to the environment, specific environment, so that we can thrive in that environment. So therefore, epigenetics just influences which part of your genome or your DNA will be used so that you can thrive.
Right. So I guess the assumption, maybe it's not an assumption, but one of the underlying principles of epigenetics would suggest that there's a huge amount of potential stored within our genes that is waiting to be activated by a given stimulus or a given change of environment, and that at this point in time, at least, we really have no idea how much potential there is being stored, right? Because it only presents itself when it is needed or required by the change in environment. Is that correct to say that?
I actually really like the way you're describing it. Yeah, absolutely. That's exactly. I actually honestly wouldn't think of it that way, but conceptually it totally makes sense.
Right.
There's a stored potential that allows you to determine how a given cell will respond, but each cell can respond differently. But nevertheless, how each cell will respond comes from the same program.
Right.
So each cell, and we have many different types of cell, they evolve to be what they are from that same program, and then they will respond to the environment based on that program. But each cell, different type of cell, will use that program differently, even though they all have the same program inside. So calling it as a stored potential, yeah, I think that's definitely very valid.
Yeah, no,
I like it.
Yeah, thanks. I'm sure other people have thought of that. It's certainly not original to me. But it's interesting because it's like, yeah, it makes sense because we have all kinds of cells in our makeup, right? You just need to think of any given organ or system in the body, and it is molecularly very different and serves different functions, and yet it all comes from the same DNA. Now, I don't know how the cells know how to do that. That seems like magic to me. The fact that it just, from a single cell, as you say, from like the first day of an embryo or whatever it's called, from the first moment when the sperm and egg become what's that called? Something...
like a zygote?
Yeah, zygote, that's the word. That
Then
all of a sudden it
eventually that transforms into embryo.
It's magic for real. That's how I think of it, because it just seems so crazy.
It is quite magical.
Yeah.
Because it's all responding to usually chemical reactions. So there is usually some molecule is touching receptors on the outside of the cell, and the cell will be responding to that stimuli. There can be other stimuli as well. So there could be electrical stimuli as well. But usually there is something touching the cell recognizes that, and then there's a built-in mechanism inside to be able to respond to that touch, and as a consequence convey that message into the nucleus of the cell, which would be like the brain of the cell, and that will influence which genetic information is used within that nucleus, which then will determine how the cell will respond. Some of it can bypass that as well. It doesn't always have to be going as deep as nuclear response, but since we're talking about genetics, that's one of it. Some of it can be immediate based on what chemicals or metabolites might be present within the cell, and that might already be responding to the outside environment. But then if you think about it, it's an incredibly complex orchestra of different chemical reactions is what is happening. And that response, that had to be programmed in first. And that's where your genome comes in.
Yeah.
So then
It's
you can
really
appreciate,
amazing.
if you think of genome as a program code, how incredibly complex that is. Because we are still quite far removed from being able to duplicate it. We have started doing this, us as in like humanity, scientists, but we are still very far removed from being able to know how to control it. Once we do, we might be able to create our own organic machines. So you brought up the example of us. We're just simply very complicated organic machines. That's exactly how I think of us.
Yeah.
And then one day, if we grasp the full potential of how to regulate genetic information, we might be able to build our own organic robots or basically create brand new species.
Yeah. And it's almost impossible to even imagine what that could be like. Because, I mean, it's not, you can think of various possibilities, but the range of what's possible is effectively limitless in terms of if we were able to really understand how it works and fits together and to be able to make a program like that. It's crazy.
So imagine the house you live in actually is a living organism.
Yeah.
So think of the same walls and windows and doors and so on, but it's actually alive. So like that. I don't know whether we'll ever do that, but then imagine if we had that capacity by having the depth of understanding of how to manipulate genetic code to build new molecular robots. And that serves us. Or think of, maybe that's too abstract, think of an engine that runs anything being organic as opposed to made out of metal and plastic and so on.
Right. And so the distinction that humanity, let's say, makes between organic and non-organic is that the presence of DNA or RNA potentially as well. But is that really what separates organic from non-organic?
Yeah, I think so, actually. That's right. All replicating organisms will need genetic information. So I say replicating organisms because depends on how we choose to define what is alive versus not. Viruses, there's an argument, are viruses alive or not? Because they do need a host to be replicated. Therefore, you can claim they don't have their own capacity to replicate themselves. But nevertheless, they can be replicated by other hosts. But let's just ignore that and let's say viruses are alive. Then, yeah, you would need that program code for a replication to take place.
Yeah, I mean, the sort of philosophical...
At the same time, I suppose one day we could create non-organic robots that could actually rebuild themselves and replicate themselves as well. So maybe that's not the ideal definition to differentiate between them either.
Yeah, I suppose you...
But I actually think we're more likely to succeed building organic robots sooner than non-organic robots that replicate themselves.
Right. It's interesting that replication is the central part of how we think of life, right? And we see it anywhere in the living world. It's about, birth, survival, reproduction, which is replication, and then death. And then that's basically the life cycle of any creature. I mean, maybe not so straightforwardly for things like cells, because they kind of go from one into two, and then it's kind of philosophically complicated to see, has that first cell died, or has it become two cells, or it's a little bit more complicated. But what's interesting is like and this is this is a sort of an unanswered question, so I'm not expecting you to have an answer to this, but what fascinates me is like, if you take any physical material and you reduce it into its real atomic level structures, right? It's all the same, basically. And yet, when it comes together in particular arrangements, for whatever reason, some of it's organic and some of it's not. Some of it does magic with DNA, and others are just rocks and water and things like that. And it's so crazy to think about the implication of where that potentially even came from, right? Like the origins of DNA, which, as far as I know, we're not exactly sure about how DNA came to exist.
Right. I haven't touched on that subject in a very long time.
Yeah.
So the last time I was hearing, and this would have been a long time ago, it's this whole chemical soup theory.
Right.
But of course, we cannot fully know, because we can only theorize, because we can look back and observe it. We can try to replicate it. I'm not sure if we've done this, to be honest, whether you mix specific constituents, but yeah, it had to probably start with something extremely simple that had the capacity to drive its own interaction, and then somehow that had to lead to being able to duplicate. But there's a reason why it had to take billions of years in order to get to where we are.
Yeah,
just
that's
because of the time required for this randomness to become so exquisitely complex in the end. Unless you like to believe that there has been intervention anywhere along the way.
Yeah, that's true. It doesn't negate the argument entirely. It just takes it one step further, right? And that's what people usually go with when trying to use the scientific method to approach, the theory of creation of everything. It's like, yeah, okay, well, if God created DNA, who created God? It's like, it's complicated, and that's for a discussion that's not for right now. But it's a crazy world. So let me ask you, the work that you're doing at the moment, right? How are you hoping to help people with this genome sequencing?
So I would divide anyone in the world into maybe two categories. Those who present symptoms of specific health issue and those who do not. So those who present symptoms is maybe easier conceptually to understand how this technology can help them. And within those who present symptoms, I subdivide them further into two categories where genetic testing is very useful. Number one is cancer patients. And the reason why is because cancer is a disease of malfunctioning genetics. And therefore, you can probe what that information is to learn more about what is driving the cancer. There are numerous potential values of that. Of course, the one that we would want to be able to gain the most is to learn further how can we treat that cancer. And that's really the power of genetics in this case, because if you're applying genetic testing in cancer, it's truly to determine as much as possible with current limitations of our knowledge is how can we treat specific cancer. And the reason why is because if you think of cancer, cancer is an individual disease. Every single person has their own unique cancer. Because cancer is like your genome that is somewhat altered, and how that genome is altered to produce cancerous state will be individual based on your own genome, right? So every cancer is unique. So then you can probe into the genetic information of cancer to see what can we do to help. So that cancer is one group. The second group would be individuals who have a condition that has not yet been identified by current medical standards, and that's more common than people realize. So an example would be is someone who is afflicted by condition and doctors really have not been able to pinpoint us what that condition is, because the complexity of the symptoms might not help to identify it outright, and might not help to identify outright what the condition is. And it also might not identify what tests should be even used for us to find out what the problem is. And this happens, this is not uncommon, when some individuals have a disease and they might spend a decade or even more of their life trying to figure out what is this problem they're afflicted with, because medical services cannot really solve it for them. Now, this is where power of genomics comes in and is very handy, is because such individuals, when they decode their genomes, you can then potentially pinpoint the problem based on finding specific mutations in that genome.
So,
and this is very frequently the case, meaning approximately maybe 50% of the time, if a person who cannot obtain diagnosis through our current medical standards, if they decode the genome, they have about 50% chance they will actually come across a diagnosis. So that's the group that presents with the symptoms. People who do not have symptoms, then that's people, like say you and I, we're presumed healthy individuals, where the potential of looking at our genome is that you can look whether we have any predispositions to health conditions or health problems, or whether we outright have a disease that simply have not yet materialized, because it might be materializing later in life. So that would be the other benefit. So this one is more to be able to satisfy your curiosity. If you're brave enough and you can withstand that mental pressure of knowing upfront. But then if you do know upfront, then in many instances, you have interventions available to you. And learning about cancer predisposition is a perfect example. Another common problems is learning about different heart conditions that people might have. If you think of the most common problems afflicting our society, the most common reasons why people end up in a hospital, or even the most common reasons why people die, there are also the most common genetic problems we encounter in our population. Not a surprise. That doesn't mean everyone has it, obviously. But someone out of a population has it, and you can identify that up front.
And so, so I guess the non-symptomatic population, it's really a matter of being proactive about health, right? And seeing, okay, well, what am I at risk for, and how can I take steps to lower my chance of this happening as best I can? Or if there is a hello dog, if there is a problem that's evident, then you can take steps to early intervention, as they would say in medicine, right? So instead of waiting for it to get severe and, impairing, you can sort of take proactive steps. But it's so, could you maybe give an example of what exactly do you find when you're looking, let's take cancer as an example, right? So when someone with cancer comes to you and says, I need to figure out what this is, or what's the genetic problem, right? What might you find in the genome?
Sorry about the background noise.
No, it's just dogs.
give it a moment for docs to settle down.
Yeah, no worries.
So cancer predisposition in presumed healthy individuals. So it's people who don't have any obvious issues. They look healthy, etc. If we were to screen such a population, the most common problem you're going to discover is indeed cancer predisposition. By far, that's the biggest one. And first of all, how often do you find these problems? It really depends on which studies you look at, but roughly, maybe I think it's safe to say approximately 5% of the time you will discover some pathogenic mutations, meaning mutations that we already know they can lead to certain clinical negative outcomes. That doesn't mean it's guaranteed, but we already know that it can. Whether it does or not, that's referred to as disease penetrance, and medicine is still trying to figure out as to why sometimes same mutation in one individual will lead to a disease and in another one it will not. But approximately 5% of the time, if you screen healthy population, you will find mutations, or in scientific jargon, it's called variants, just like we call virus variants. They're different mutations of themselves.
Yeah.
Mutations are not often used in scientific literature. It's called variants. Then we can learn there's predispositions, and of what we find out most frequently is cancer predisposition. That's probably going to be somewhere in the order of maybe 30% of the time. If we find problems, it will be something related to cancer. Breast and ovarian cancer, so BRCA1, BRCA2 are by far the most common problems discovered. Another one that is very high in the top is Lynch syndrome. So that's a genetic predisposition to colorectal cancer. That's a very good example of very high value information, because colorectal cancer can be very deadly if it's discovered late in a stage of cancer. And unfortunately, because of where that cancer evolves or develops, usually it is discovered quite late. And then chances of survival decrease rapidly. But if you know the genetic information up front, that you have a genetic predisposition, then you have the freedom to be able to screen yourself more regularly for this particular problem in the future. And if the cancer does indeed develop, then you have the possibility of catching it very early on. And the ability to then treat the cancer successfully is dramatically improved.
Right.
We're talking about order of magnitude better chances of survival for such individuals. So this is a really good example. So cancer is usually the top problems discovered. The second top problems is problems of heart diseases, so heart conditions, where we're talking about arrhythmias. We're talking about issues with proper heart functions. So we can have issues where heart is not properly developed. Sometimes you hear of athletes dropping dead. So when that happens, we've heard that more about that more recently, but that has existed before. And when that happens, it's not unreasonable to suspect there might have been a genetic predisposition that has led to inappropriate heart development, and that heart was simply not used properly in such individual. So that individual probably should not have been doing such high output activity for the problematic heart.
Right.
So I'm just coming up with some examples.
Yeah.
There's a plethora of different heart conditions that can be uncovered. So those are the ones that are most commonly uncovered. Heart conditions and cancer conditions. And then it can trickle down to many, many different conditions. Literally, when you sequence your genome, in theory, you can test yourself for thousands of conditions. So it depends on who the provider is. Typically, you're not going to get information for thousands of conditions because some of them are not maybe fully validated yet to such a degree that we can feel very confident presenting that information yet. But well over 1,000 conditions, we could probably be able to successfully diagnose that, hey, this could potentially be an issue in the future because we already know that these genes are implicated in these problems.
Right. And there's also neurological conditions, right? It's like screening for
Correct.
neurological things.
Thanks for bringing that up.
Yeah.
That's another common one. Yes.
Yeah. And I think that would,
So
I don't know which one I would be more afraid of, neurological or a heart condition. Probably neurological, but that's probably just my imagining that it's worse to have a brain disorder than a heart disorder, which may or may not be true. It just feels like it would be. But I mean, if your heart stops, you're dead. Right. It's not like you can just disregard the heart.
Right. Yeah, imagine sometimes that's the very first symptom of your disease is the fact that someone literally dropped dead, which really does happen. Unbelievable.
Yeah.
I never think of fear when I think of these issues because there's a gradient. So you have neurodevelopmental conditions. Some of them can be milder in what they lead to, and some of them can be very debilitating. And it's the same thing for cancer, and it's the same thing for heart issues. Really, it comes down to whether a person, but fear obviously plays a very big role, and this is exactly why sequencing genomes or sequencing your DNA is not for everyone. If a person is an individual who has a high propensity to very high level of anxiety, you might not want to be looking into your genetics, and I think that's understandable.
Yeah.
But if you're a person who can handle information, including learning bad news, and you can handle it and you're gonna move forward, then that's something that I would always recommend.
Yeah.
Obviously, I decoded my genome.
Yeah.
Obviously. And I remember going to the doctor to get my report and find out. And I requested to be screened for everything, including Huntington's condition, which is very debilitating. And I was scared going to a doctor. I was ready, but I was scared. I was like, hey, am I going to find out I have a problem that while I'm thinking I'm completely normal, am I going to find out that my life will change as of today, moving forward?
Yeah.
So I was scared, but at the same time, I was ready for it and deal with it. If there was an intervention available to me, because sometimes you might find out you have a condition and there's no treatment available of any kind, no intervention, not even management options.
Yeah.
So Huntington's is a good example. You just find out that you're going to have this very debilitating condition, the onset of which is sometime later in life.
Yeah.
It's not a welcome news, obviously, right? And therefore, that's not for everyone.
Yeah, that would be like worst case scenario, I would imagine, is you find out that something bad is really going to happen to you, perhaps that you've never even heard of, but now you know, and that there's nothing that can be done about it. That would be rough. But I mean, that's probably rare in occurrence, hence why there's no management or treatment options. Generally, those are the rare disorders. There's no funding for that, but it's a medical ethical question. But it's interesting, the relationship between between one's view of knowing and not knowing, right? Because on a day-to-day basis, we tend to operate pretty disconnected from all of the potentially bad things that could happen to us. Even in highly anxious individuals, they're sort of focused on a few bad things that could happen. But, to think about every bad thing that could possibly happen to you, medically or otherwise, I mean, you would just have nothing left. There would be no brain power left, if that was what you were thinking about all the time. And, there's a rational argument that it's better to know and do something and potentially do something about it than to not know and then just have it hit you like a truck. But I also understand why, you wouldn't want that, and you might prefer to just not know and see what happens. It's a good point. It's complicated, and I guess that, you know, a lot of people will, once something has happened, then they're like, well, now I need to know what this is, which is fair enough because you need to know how to deal with it. So do you see more symptomatic clients rather than just like the proactive kind? There's a bit of both.
Overall, what would be it's interesting because I actually didn't even think of it, which group is more frequently. It's more at 50-50. If I think of all the different types of DNA tests, then it's maybe even.
Yeah. Fair
maybe
enough.
even. But to your point, you know, I was smiling when you were just making your comment because it's true what you're saying. I actually had what would be self-proclaimed hypochondriacs reach out to me and tell me, yes, I'm scared of everything, so I at least want to know what I should be scared of, as opposed to be scared of everything. So at least I can focus my fear and worry on a specific condition, as opposed to right now, because I don't know what to be afraid of, and that's part of my nature, is to worry about what's coming. At least this will give me a focus on as to what to worry about, and then try to manage that. Wow. So that's why when you were talking about this, it reminded me of that, because that's not something I ever thought of when I wanted to offer access to these technologies.
Yeah,
that's the
makes sense. Point. It makes sense.
But at the same time, yes, some people. To me, it makes sense. I'm not necessarily worried, but why did I decode my genome? Is to find out, is there anything I should be taking care of? The really big ones is the ones where of high value is when you learn of conditions where the intervention is available, and there's many of these.
Right.
And the ones that are uncovered most frequently, if you presumed healthy individuals, those often happen to be the ones where we have interventions available.
Right.
Hence, you can appreciate that, why it's of value. That's why I often am told by people, oh, I'd rather not know and therefore not worry. And then I always respond with a question, but what if I could tell you just the information where you can find out it leads to a problem, but we have intervention available for you right now. Would you want that kind of information? And only that. So don't find out about information where there is no treatment available. Maybe ignore that. You could still just request information that has intervention available for the conditions we will be uncovering.
And what did they say? Did they say they would want to know?
It's half. Maybe some people still like, oh, ignorance is a bliss, and I respect that. Again, it depends on person's mental fortitude of dealing with negative information, and it totally needs to be respected. And some people are like, oh, in that case, because then if I can do something about it right away, then why not?
And I agree, and you got to respect what people want. I mean, the biodiversity of humanity is why, you know, we're so great. Well, I mean, of every species, but, you know, human centrism is pretty frequent. But there's also this area of pharmacogenetic testing, right, which basically tells you how your body will respond to certain medications or drugs, and which ones you'll respond to well, which ones you'll respond to averagely, and which ones you'll respond to poorly or adversely, you know, which is I think a lot more like readily applicable to everyone's kind of life, right? Because it would be great to go to the doctor and say, well, you know, you go to the doctor, they tell you you have something, right, whatever it is. And then, you know, in their head, they have maybe 10 or 20 different options of what medications to prescribe to you. And they'll use their clinical judgment to make the best choice based on evidence and clinical judgment of what's most likely to work. And that's a pretty good system, But it's even better when you can go in with a sheet of paper that says, well, we can definitely rule out these ones, because that's only going to make the problem worse, or at least do nothing and reduce it to, these few options. So do you have a lot of people that come for that kind of testing as well?
Yes, pharmacogenetic testing is the most frequently purchased test through Merogenomics catalog. And in my opinion, it is one of the most useful ones.
Yeah.
It is a cheaper test because, of course, you're only analyzing fragment of your full genome's information. It is almost always actionable. Everyone will get some results of value, because everyone will learn, hey, how do my genetics align with medications? Or in other words, based on my genetics, how is my metabolism influencing the medications I'm taking? And that's very valuable, because then you can determine which medications you should be taking. And then when you're taking those medications, whether you are taking correct dose or not.
Yeah.
Because if you're poor metabolizer or a fast metabolizer, you might need to adjust your dose for this medication to even be effective. So without that information, the medication might seem ineffective or problematic, when really all that happened is you just took a wrong amount. So that's down the road. I think pharmacogenetic testing is one of the most valuable DNA tests an individual can take. And it is my wholehearted dream that eventually literally every doctor will be offering it in their clinics. Because imagine how valuable that is for a doctor, knowing that kind of information granularly for their patients. Oh, I have a list of medications that we can link to your genetics, and this information tells me, avoid these medications, it's going to be outright problem. Well, let's avoid the problem in the first place.
Yeah.
Right. And then you still have to confirm whether the genetics does indeed correlate with the actual outcome. So you still have to obviously carefully monitor when you determine the dose, what is the outcome, and respond afterwards. That's what doctors are already doing. When they assign you a medication dose, they have to now follow that carefully to determine, do we need to decrease that dose or increase it? But at least that very first application is less random than what we're currently doing. And that is especially valuable for mental health medications. Yeah. Because in pharmacogenetics, mental health medications constitutes the largest group of pharmacogenetic medications, meaning medications that we have worked out how to be linked to your genetics. And number two, from my personal experience with my own clients, everyone gets a hit in mental health medications. But another big group is cancer. Pharmacogenetics has information related to many different medical specialties. Just what happens is that mental health is the biggest one. Cancer is, I believe, close second. Cardiology, in medications for infectious agents, and so on. But there's many different medical specialties that are covered by pharmacogenetic testing, so you can see how valuable that is. And you just need to take that test once, right, and you get that information. Not an expensive test, easy to interpret. Yeah, that's the one that I really think will be one of the ones that will really be transformative prior to full genome, which is much more expensive.
Yeah, I mean, I take mine with me when I go see the doctor or the psychiatrist. I mean, they have them on file now, but I did before, and it's just a game changer. And the problem is, like, I mean, I think the reason why, mental health medication or psychopharmacology or whatever it's technically called is so, important to people, never mind the huge amount of mental health issues that people have, that's a given, but the fact that they're so powerful in terms of adjusting our sort of psychophysiological states. And often, you might see on your antidepressant that there's risk of it making it worse, or, creating a deeper depression or suicidal ideation or panic attacks, or there's always that risk. And so by having a test or by having your the genome sequence, you can at least say, okay, well, I must definitely avoid these ones, right? Because I don't need to do that. And luckily we're in a position medically, humanity is in a position medically where in each class of drugs, there's multiple options that come from different families or whatever. And so if one doesn't work, it doesn't mean that's the end of the line for you. It just means you might need to try something else. And again, I guess, your point is valid. It's not like this test tells you that it's definitely going to work for you in this specific amount. And, you don't need to know anything else. It's like, no, but it screens out a lot of the trial and error that is often accompanied with antidepressants or anti-anxiety medication, which could save people a huge amount of, unnecessary suffering between the transition periods and, whatever else comes with it. And so it is great. And the doctors are always surprised when I present it to them. They're like, oh, that's cool. Where'd you get this? And then I tell them and they're like, oh, okay, that's cool. And it helps them, because they would like to know this for everyone. I mean, I guess in an ideal world, right, when a child is born, they get a test and then that's on their medical records. And then all medical treatments in the future will be, based or used in conjunction with the genome sequencing. Maybe we're a few years away from that, but that would be nice.
I totally believe that's going to happen.
Yeah.
I believe eventually every single newborn will have their full genome sequenced upon birth, precisely because of the value of information it's going for the health benefit of that individual will be so high. And value for society as well, because it's much cheaper if we can intervene right away as opposed to dealing with an outcome later on where it's much more difficult to manage and then potentially also even try to figure out what the issue is. There is a reason why we have already newborn screening. So we are already employing not full genome sequencing, but every single child that's born, immediately they have different biochemical tests performed for some of the most common early onset diseases or conditions. And that's precisely to try to avoid issues later on.
Yeah.
And full genome would do something very similar, but far, far broader.
Yeah. No.
So I do believe this is coming and it will be part of our medicine, like standard.
Yeah. Well, I look forward to that. Thank you very much. This has been a really great conversation. I'll put links in the description as well, but, please plug your company and your pages or whatever you would like.
So Merogenomics.ca is the website where you can learn about DNA testing. That's MERO, genomics with an S at the end, .ca. It's a great resource for anyone doing any type of DNA testing because it's just simply good educational information, and everyone should educate themselves prior to taking any DNA test just because of the power of information that is being investigated. Even if you're doing something as seemingly trivial as ancestry, there's nothing trivial about that because your still genetic code is being looked at. And then, of course, you can also look at what kind of DNA tests are available for medical interpretation, where, of course, I believe is the greatest value. On top of that, we have a great YouTube channel where we teach about different science topics. We're especially focused on COVID-19 because that's where the big interest is. So again, that's Merogenomics. You can find us on pretty much all main social media platforms, Twitter, LinkedIn, Facebook.
Yeah.
But in terms of you're looking for educational content, the website, Merogenomics.ca, and the YouTube channel, Merogenomics as well.
Awesome. Well, thank you very much. I encourage everyone to check that out, and I look forward to speaking with you again soon. All right. Take care.
Likewise, this was a pleasure and really, really fantastic questions. You clearly have in-depth knowledge of this topic, so this is a pleasure. Thank you very much for this experience.
Thanks, man.
I really enjoyed this.
I appreciate it.
Bye for now.
Okay. I pressed